Hi everyone, I welcome you all to my channel Econopatsala. I have started a new series of sessions on econometrics. This is the second session in which I'll be discussing about estimating an econometric model using OLS. In previous sessions, I have already flagged the importance of econometrics, econometrics meaning economic measurement, and this has emerged as a very popular tool to undertake empirical analysis for writing PhD thesis, for writing research papers, not only in economics. It is no more confined to economics research. It is spread over to other disciplines like commerce, business management, social science, and even medical studies. And econometrics also is popularly used for supporting informed policy decision by the public authorities, different government agencies, also in the private decision making process. So that's how econometrics has emerged as a very popular empirical analytical tool. So in the previous session, I had discussed about a specification of a econometric model. So for specifying an econometric model, we require theoretical underpinnings drawing from the respective discipline. Say I discussed about the law of demand, Keynesian consumption function, drawing from economics. Similarly, from your own discipline, you can basically think of the logic, the intuition behind building your empirical model, which can be used for econometric analysis. So in general, your econometric model can take a form as given in the equation, where y will be the dependent variable or explained variable or left hand side variable. So the dependent variable is the variable of concern, the behavior of which you want to analyze. So for example, if I'm talking about law of demand, I'm trying to understand how people demand or purchase quantities of various goods and services based on several parameters. Uh, those parameters on the right hand side can be x1, x2, x3. We call them independent variable, explanatory variable, exogenous variable, or right hand side variables. Say if I want to explain the consumption demand, the uh, the behavior of the households to purchase various goods and services, and there y is my demand for various goods and services, then my x's, my explanatory variables, can be income of the household, prices of goods and services, wealth of the individual, okay, family size of the household. So this way we can think of different variables on the right hand side which act as the explanatory variables to explain the behavior of the left hand side variable. So you can refer to my previous video to sort of have a broad understanding about how we specify an econometric model, and I have already discussed in that the importance of u on the right hand side, which I term as stochastic error term or stochastic disturbance term, which is of greatest importance in econometric analysis. Now, after specifying the econometric model and before undertaking estimation, what is required is data. We need to have data on the dependent variable y, explanatory variables x1, x2, etc. So only once we have data on those variables, then only we can go to next step of estimating the econometric model. So today I'll be discussing, broadly there are two sets of methods which are used for estimating an econometric model. One set of method are popularly known as maximum likelihood estimation method. Okay, and the other set of methods are least square method. So least square methods are relatively simple, and the OLS, ordinary least square, which I'll be discussing with you today, it is a variety of least square methods. And today I'll be using a simple econometric model for explaining estimation of an econometric model. And by simple econometric model, what I mean, I restrict to only one right hand side variable. So as you can see in this econometric model, I have my y is the dependent variable and only x1, only one explanatory variable appearing on the right hand side. This is basically simple or two variable econometric model. And as I have already indicated earlier in my previous session, beta 0 is your the intercept and beta 1 is the slope coefficient. And in most of econometric analysis, the focus of the researcher or the analyst is about the estimate of beta 1. So beta 0 will have a meaningful interpretation in our econometric analysis only if you have a large number of values of x1 which are closer to 0. And in most of the examples in economics, the values of right hand side variables will be quite different from 0. Like if I'm talking about GDP, it is some lakhs and crores. I talk about CPI, consumer price index, it will be 100, 112, 113, something like that. Okay, so we don't have adequate number of observations of the right hand side variable if it is GDP, if it is CPI, if it is interest rate, if it is population, which will be closer to 0. So then beta 0, the intercept coefficient, doesn't have much meaning in our econometric analysis. Okay, so largely our inferences will be on the beta 1, estimates of beta 1. Now, as I said, once we specify the model, the next thing is to collect data. So in this simple econometric model, two variable model, I have two variables: credit growth, assume it is bank credit growth, which is given in percentage. That's my dependent variable y, and net NPA, non-performing asset, net non-performing assets, that is again in percentage, is my right-hand side variable x1. So before I start the econometric estimation procedure, a good way to start is trying to plot these variables in a scatter plot, as you can see. Now, once we look at the scatter plot, uh, what we can conclude about the impact of net NPAs on credit growth. Basically, what is the type of relationship they have? Do you think there is a positive relation, there is a negative relation, or no relation? So the question is, do the NPA levels of bank impact their credit growth? Okay, so if there is an impact, is it positive or it is negative? Okay, so that is what the research question we are asking. So looking at this scatter plot, it is very difficult to decipher and convincingly conclude about the impact of NPS on credit growth, right? So to have an objective analysis on the relationship, we have to use an econometric model. So by econometric model, what I mean, can we fit a straight line which can explain the relation between bank NPS and credit growth in the best possible manner? Now, if we don't have an objective criteria, different individuals, they can draw different inferences from this scatter plot, which portray the relationship between net NPS and bank credit growth. So someone can perhaps fit a straight line like the black line, which is relatively flatter. Some can fit a line like the orange color line, which is relatively steeper compared to the black line, or someone can fit a line like the green line, which is the steepest among the three. Okay, so now based on our subjective observation, if someone is fitting a line like the black line, perhaps he doesn't see any relationship or any significant impact of change in NPA on bank credit growth. As you can see, although the bank credit growth is sort of ranging from 2% to 12% broadly, you see there is not much change in the credit growth if I am fitting a line like the black line to explain the relationship between bank NPS and bank credit growth. On the other hand, someone who is fitting a straight line like the green line, okay, see a significant negative impact of change in bank NPS on the credit growth. Particularly, the negative relation between bank NPS and credit growth becomes pronounced if somebody is fitting a straight line like the green line. So, as a researcher, we don't want to leave the inference on the impact of bank NPS on credit growth to the subjective discretion of the researcher. The best way is, can we think of a scientific way which is objective and which is more of convincing and acceptable to all to explain the impact of NPS on bank credit growth looking at the graph in front of you. So for that, we are basically gradually moving towards OLS, which is a very scientific and objective method to capture the impact of NPS change on bank credit growth. So in this graph, what I'm trying to do, assume we are thinking of two possible straight lines like the orange color line and black line, which perhaps explain the relation between bank NPS and credit growth. To develop an objective criteria, what we can do, let us take the case of black line. We'll calculate the vertical distance between each point on this scatter plot and the black line. As you can see, I am showing this here, the black dotted vertical line here, my cursor you can see, and the another one is this. So these are basically 2 points I have chosen, but one can choose one can basically draw similar vertical lines from each of the points in the scatter plot to the distance between that point and the vertical distance between that point and the black line, and then sort of add them all, and if the vertical sum of the vertical distance is large, that perhaps suggests that the black line is not good enough to explain the relation between NPS and credit growth, which is observed from the scatter plot, right? Alternatively, similar vertical distance from each point to the yellow color line can be computed, and for once it is computed for each of the points, then it can be added up. So that will give us the sum of vertical distance, which will say, let us interpret as deviation from the point on the scatter plot to that respective line. Okay, and say if I'm choosing between the yellow line and the black line, I'll be calculating the sum of such deviations from each point with respect to the black line, and similarly from the yellow line, and compare the sum of distance between them. So in the yellow box you can see here di says deviation. I'm calculating this is vertical deviation as yi, that is the point in the scatter plot. Each of the point, I stands for all the points 1 2 3 4. If I am having here roughly say 30 banks, then bank number 1 is where I is taking the value 1, bank number 2 I is taking the value 2. So this way yi stands for the point on this scatter plot, okay, and then beta 0 minus beta 1 xi stands for each of the straight line which I'm fitting. So assume for this yellow line, the beta 0 is the intercept of this yellow line, and beta 1 is the slope of this yellow line. Similarly for the black line, beta 0 will be intercept of the black line, and similarly the slope of this black line. So that way, the in the yellow box on the right hand side, beta 0 plus beta 1 x that basically, I'm sorry, it should be plus. Okay, here the relation is negative, so that's why it's negative. Otherwise, the beta 0 plus beta 1 xi in general will represent the straight line. Okay, and the coefficient, the sign of coefficient beta 1 is negative because we are talking about negative slope of these lines, right? So the vertical distance between each point and the respective line which we can think of, alternative lines which we can think of, okay, measure sort of the error representing the failure of the respective line to explain the relation between NPAs and bank credit growth as given in the scatter plot. So if the sum of this error is minimum, then it is good. So if I'm thinking of these two lines possible, say the sum of error for the yellow line is say A, and the sum of error for the black line is B, and if A is less than B, then I'll interpret that the yellow line fits the relation between NPA and credit growth as given in the scatter plot better way compared to the black line. Now the issue is, if we keep on drawing similar lines like yellow line and black line, which can explain the relation between NPAs and credit growth as given in this scatter plot, there are infinite possible lines, right? So each individual can have a different way of explaining the relation between NPAs and credit growth fitting a particular line according to her subjective interpretation. So this way, there are infinite lines possible. And now, if we'll be sitting and keep on calculating the sum of distance of the respective point from that respective line, then it will be a time consuming, tedious, unending process. And then obviously it will be impossible to compare the sum of distance for respective lines and find which is minimum. That is problem number one. Problem number two, when we are calculating the sum of distance this way, some distances will be positive, some distances will be negative. So when we add up, perhaps the sum of those deviations will not be comparable. It may be possible that the deviations for a particular line, individual deviations are quite large, but if they're balancing in terms of positive deviations and negative deviations, the sum can be minimum. On the contrary, there could be a line which is fitting the scatter plot in a better way, but if all deviations are positive, then the sum of deviations will be a larger number compared to the first line I'm referring to. So to avoid this type of problem, a better way is possibly to take square of deviations, this di, for each of the point for the respective lines, and then sum it up. So when we do squaring of deviation, square will be always a positive number. So across all the points, the deviation square will be positive, right? So then when we add up for different lines, then the comparability will be better. Then secondly, the when we take square, the sum of squares, each square penalizes the larger deviations more compared to smaller deviations. So that will be objective way of trying to find out a straight line which fits the scatter plot in the best possible manner. So what I'm trying to tell you, one criteria is counting distance 1, distance 2, the like I'm representing as d1, d2 up to dn for n points, and take a sum which I'm denoting as summation d, okay, and calculate this for different lines and find which one is minimum. But compared to that, a better strategy will be take square of such deviations like d1 square, d2 square, d3 square up to dn square, and take sum of square of these deviations, okay, which I'm telling least squares or ordinary least squares, right? Now this sum of ordinary least squares will be better compared to sum of deviations because the second one, there will be no cancellation of positive negative deviations when we take square, and secondly, the larger deviations will be penalized heavily. So on these both account, if we want to objectively choose a straight line which best explains the relation between bank NPAs and credit growth in the previous graph, it is better to adopt a strategy which is sum of d square, or which is square of d1 plus square of d2, etc., up to square of dn, and calculate that for each line, and for the line for which this sum of squares is minimum, that is perhaps can be chosen as the best possible line explaining the relation between bank NPAs and bank credit growth. Okay. Now the question is, again here the problem remains, when you have n possible lines explaining the scatter plot in the process of a least square procedure, right? Then we have to spend endless time in computing those sum of squares for those infinite lines, and ultimately will not uh, come up with a conclusion calculating which is the best, because there are infinite possibilities. So there we'll be using mathematical method, particularly mathematical method of calculus, okay, for trying to find out that among different sum of squares which are corresponding to different possible lines explaining this scatter plot, which one is the minimum. Okay, so from differentiation, I mean from the calculus, we know the on constant optimization which we follow, the first order condition for minimization is the sum of squares of d, okay, when we take partial derivative of that with respect to beta 1 as well as beta 2, okay, those partial derivatives should be equal to 1. What I'm trying to tell you, we need not calculate sum of squares for each line manually and trying to compare. That anyway will not lead to any solution. So we are taking help of calculus and using the optimization principle, particularly from on constant optimization. The first order condition suggests that for a minimization, the first order partial derivative with respect to beta 1 beta 2 should beta 0 beta 1 here should be equal to 0. So the first order condition is given by partial derivative of summation of d square with respect to beta 1 in the first equation here. Okay, this should be equal to 0. So using this, if we do we undertake necessary mathematical manipulation, finally we'll get the formula for beta 1 as given here. See, formula for beta 1 from this minimization principle using calculus, we can get as beta 1 is equal to summation yxi over summation xi square. Here y, xi are in lower case, and the definition of lower case is given here. So lowercase yi is equal to yi minus y mean. Here y bar actually, okay. The y mean in the second term on the right hand side is y bar, which is basically mean of yi. See, let me explain. See here, I have data for say nearly 30 banks, right? So for first bank, credit growth may be 10%. Capital yi is equal to 10. For the second bank, assume it is 12%. So y2 is equal to 12. So for 30 banks, I'm calculating what is the mean value. Assume that mean value is 11, okay, which is given by y bar on the right hand side here. Okay, so lowercase yi is equal to capital YI, that is individual banks credit growth, minus average credit growth of all the banks in the sample. Similarly, I can calculate lowercase xi is equal to capital Xi minus x bar or x mean. Okay, so here capital Xi is NPA of the respective bank. Maybe for the first bank, the NPA level could be 4%. So x1 is equal to 4. For the second bank, xi could be 3%. So in that case, my x2 will be equal to 3. So if I take average of all these x1, x2, x3, xn, etc., so I will get the mean value which is given by x bar, capital X bar, on the right hand side here. Okay, say here, I hope you are able to see my cursor, this term. Okay, so this can be say 5%. So that way, capital Xi minus mean value of xs, which is basically x bar, gives me lowercase xi. So from the minimization principle, from the first order condition, we can derive the formula for beta 1 is equal to summation lowercase yi xi over summation xi square. Similarly, from the first order condition, by taking partial derivative of summation d square with respect to beta 0, okay, in the second bullet here, okay, and setting it equal to 0, okay, I get beta 0 is equal to y bar minus beta 1 x bar. So here it is y bar, okay, mean of y bar minus beta 1 x bar. Right, so beta 1 value we have already got in the first bullet, and we have the sample of y, so out of that we get the mean value of y. Sample of x, we get the mean value of x, and then using that we can calculate beta 0. So this way, using calculus, we can fit ordinary least square, and from the minimization principle, using calculus the first order condition, taking partial derivative of summation d square with respect to b1 and summation d square with respect to b0, we can obtain the formula to calculate beta 1 and beta 0. Fortunately, you need not compute these values of yi, lowercase yi, xi, beta 1, beta 0, etc. manually. Nowadays, econometric softwares are available. Once you enter the data and you give the command for running OLS, you will be getting these values of beta 1 and beta 0 in fraction of a second. And in some session, I'll be basically discussing about how to collect data, how to sort of import this data to a econometric software, and then undertake estimation using OLS. I'll be doing in a session maybe within a month or so. So if we calculate beta 0, beta 1 using OLS the way I explained, perhaps we can get a straight line like red line here, which is the best way to explain the relation between NPAs and credit growth, summarizing the relation from the scatter plot. Okay, so here 7.38 is the estimate for beta 0 and negative 1.12 is the estimate for beta 1. Right, so x is here our NPS, y is here credit growth, and this scatter plot, as I repeat, is giving the pair of relationship between credit growth and NPS for 30 banks for India around 2016, and I'm trying to use an econometric model, a simple econometric model, okay, to explain the relation between NPA and credit growth. And using OLS, I have got the slope coefficient minus 1.12, intercept coefficient 7.38, and this red line here is basically corresponding to this intercept and slope coefficient which is estimated. So this way, red line is an best possible way of explaining the relation between NPAs and credit growth, which is derived from our estimated econometric model. Similarly, if I'm thinking of Keynesian consumption function, so Keynesian consumption function in a simple regression model, that is two variable regression model, can be represented as C is equal to A plus BYU. Here C, the dependent variable, consumption, and Y is the independent or explanatory variable, income, and A is the intercept, B is the slope coefficient, and U is the stochastic error term. So this specification, as I repeat, has to be drawn from our economic theory or theory of your respective discipline, right? So once we specify the model, next step is to collect data on the left hand side variable C and on the right hand side variable Y. Then undertake OLS as I explained and estimate the intercept or slope coefficient. And if I'm using OLS using the minimization principle which I just explained, and then the estimated value of beta 0 is 3382.5 and the estimated value of beta 1 is 0.61, and this is explained here. So the scatter plot, the blue dots, they explain the relationship between per capita income and per capita consumption spending in India. So my dependent variable C is on the y-axis and my independent or explanatory variable is on the x-axis. And the scatter plot given in the blue dots explain the relation between them. So using OLS, the way I explained, applying the minimization principle, that is taking the first order partial derivative of summation d square with respect to beta 1 and beta 0 separately, I can calculate the slope coefficient as 0.61 and the intercept coefficient as 3382.5, and the straight line, red straight line which you see here represents the intercept coefficient of 3382.5 and slope coefficient of 0.61. So this is a simple way of estimating an econometric model, basically simple regression model or two variable regression model. And the estimation of a multiple regression model will be little complicated, little mathematically more involved, and in the next session I'll be discussing about it. Now the important thing is, in econometrics we are using data from a sample and getting the estimates of beta 0, beta 1. Like in the previous example, I got the estimate for the slope coefficient as 0.61. Now this 0.61 I obtained based on data which I used. So assume I have used data for say 92, 93 up to 2024-25. So for this 35 years or so, okay, if I'm using this data, maybe I'm getting the number as 0.61. Had I used say data from 1951-52 up to say 2024-25, I could have got another number, not necessarily 0.61. It could have been 0.52 or 0.73. Okay, so the important point to note is the econometric model which we estimate uses data from a specific sample. So the estimate for the slope coefficient which I got, which is 0.61 in this case, depends on which data I have used. Okay. So ultimately, as a researcher, as an economist, I want to make a conclusion that in general, if I'm talking of 2026-27, 2030-31, and not only for India, for any country, maybe for China, for Russia, for US, for Sri Lanka, do I get 0.61 everywhere, right? So if our objective is to test the Keynesian consumption function, and Keynesian consumption function suggests the value of the slope coefficient should be greater than 0, less than 1, then based on my sample estimate of 0.61, can I make an inference on that? Does this sample estimate of 0.61 help me to conclude that in general beta 1 will be greater than 0, less than 1? Is it possible? Secondly, if it has to be used for policy, the public authorities need to know what is this value of beta 1, marginal propensity to consume. Is it very strong, closer to 0.9, or it is very weak, like 0.1? Accordingly, at a time of crisis, they need to decide on the form of fiscal stimulus. Assume if MPC is very high, like say 0.9, then emphasizing a government expenditure on a government expenditure program, which will be sort of giving some extra income in the hands of the consumers, on the hands of the households, can help in getting can help in making very effective fiscal policy to revive economic growth. On the other hand, if MPC is very low, like say 0.1 or 0.05, then a massive government expenditure program stimulus may not be helpful to revive the economy quickly. So, for policy authorities, it is important to know in general what is the value of MPC. So, ultimately, the OLS analysis, which gives us a sample estimate, like for my sample, I got a value of MPC at 0.61, is not very helpful unless we are not able to make conclusion about general population parameter. Okay, so had we included data for all the years over all the countries, okay, anytime in the future, okay, should the value of MPC be closer to 0.6 or 0.9 or 0.5? That information is critical for policy analysis. So the next step after we estimate an econometric model, basically get estimate for a slope coefficient or interest rate coefficient, is to what extent what we observed for our sample, based on that, to what extent we can make a conclusion and inference about the population parameter. By population parameter, I mean the value of MPC in general, which is not limited to my sample, right? So this is a very critical step in econometric analysis. What we have discussed until now, estimation of sample estimate like beta 1 or beta 0 is fine, but that is the second step as of now after specification of the model. The next thing is to make a conclusion on population parameter, that is value of beta 1 in general for the population, where we include all data of y and x. Okay, what will be the value of that? See, the problem is in science like economics is a non-experimental science. We cannot generate data like a physics lab or chemistry lab. So whatever data is available, based on that we undertake our research, empirical research, and then infer about the relation between the variables. So in this context, it is very critical to undertake hypothesis testing and move from our sample estimate of beta 1 to the population parameter. Now, the second thing is we discussed about OLS. There could be many procedures of estimating beta 1, beta 0. As I said, broadly two sets of procedures, maximum likelihood procedures and least square procedures, and OLS is a form of least square procedure. Then if there are other estimation procedures are possible, why should we confine to OLS? The saving grace is there is a Gauss-Markov theorem which suggests that if certain classical linear regression model assumptions are satisfied, these assumptions are about properties of U and nature of X, relation between different explanatory variables on the right hand side, about which I'll have a separate session. If those assumptions are satisfied, then OLS procedure, which I discussed, will be the best linear unbiased estimator. Now, what is this best linear unbiased estimator here? As I was telling, I have chosen my sample for a particular period and I got a sample estimate of beta 1. So I have chosen my sample with a probability, say P1. Had I chosen a second sample with probability P2, I could have got a different estimate of beta 1. Okay, say that number is a 0.53. Had I chosen a third sample with probability P3, I could have got a third estimate of beta 1, which perhaps could be 0.48. So there is a random distribution of sample estimates beta 1 depending on the probability distribution of the sample which we have chosen. Let me explain again. With some probability sample 1 is chosen. With some probability P2 sample 2 could have been chosen. With some probability P3 sample 3 could have been chosen. Accordingly, I could have got first estimate, second estimate, third estimate of beta 1. So if the distribution of estimates, different estimates like number 0.1, 0.2, 0.3, etc., and their probability we can plot, and if it is a random distribution, and particularly if it is following normal distribution, right, then OLS, ordinary least square, can be the best linear unbiased estimator of the population parameter. Okay, assuming CLR, classical linear regression model CLRM assumptions are satisfied. Let me explain again. I think there is a scope of confusion. Please listen to me carefully. I am telling the probability with which I have chosen a particular sample. Accordingly, I am getting a particular estimate of beta 1. If I assume this probability distribution is a standard distribution like a normal distribution, stochastic, any stochastic or random distribution, right, then it will have a mean, it will have a variance. Okay, and if we are using OLS and classical linear regression model assumption are satisfied, then mean of these OLS sample estimates will be the population parameter. So for simplicity, assume with the sample the random distribution of the sample estimates, possibly take value of 1, 2, 3, 4, 5, 6, etc. Say up to 20. Okay, and say average of 1 to 20 is 10. Okay, so then if you are using OLS and classical linear regression model assumption are satisfied, then your sample estimate, the estimate which you will got will be equal to population parameter, which is 10 in this case. You have a sample distribution, a distribution of beta 1 values which you are getting, that may be varying from 1 to 20. Okay, and the variance, of this, the distribution, okay, distribution of sample estimates will be minimum. So applying OLS, if CLRM assumptions are satisfied, although you will be estimating a sample estimate using OLS, okay, you have the best possibility of getting the population parameter. Your sample estimate on an average will be equal to population parameter. That is what in this example, assume B1 is my sample estimate and it has a distribution, random distribution, and EB1 is the mean value of those B1s. As I said, B11 maybe the estimate you got from the first sample. B12 you got the estimate for the second sample, like B1n for the nth sample. If there is a probability distribution of these n sample estimates of beta 1, that average, that is E of B1, will be equal to beta 1, which is the population parameter, right? So if you are using OLS estimating beta 1, if CLRM assumptions are satisfied, on an average, your sample estimate will be equal to population parameter, number one. Number two, the variance will be minimum. See, when you have a statistical distribution, okay, if the average is equal to population parameter and the variance is minimum, that is the best possible option we can have. So that way, as long as CLRM assumptions are satisfied, perhaps there is no need to look for a second estimator. We can use this simple ordinary least square procedure to estimate beta 1 and beta 0, and our estimate of beta 1 will be equal to population parameter with minimum variance. So that is the best thing we can expect to conclude about the population parameter based on our sample estimate. So I hope this video was useful for you, and given the paucity of time, perhaps I could not elaborate adequately. And if you have any question, you can write me back in this video itself in your response, or you can write to me in the email given here. I'll be happy to answer your questions. Thank you.